Alright, we are on section 4.3 today, which is connecting f prime and f double prime with the graph of f, and it's one of my favorite sections, so hopefully it will be for you too. I have some quick review questions on here just for you to go through if you'd like to. I left them on the PowerPoint for you, just like normal. So we are, there we go. What we're learning about today is the first derivative test for local extrema, concavity, points of inflection, the second derivative test for local extrema, and then learning about functions from derivatives. And so it's a big section, lots to learn about, but not too bad. First derivative test for local extrema. I have a picture here of a graph, and this picture has various maxes and mins on this graph. We can see that down here at our endpoint A, we have an absolute min. That's the absolute lowest value we have. We have our absolute max up here, and you can see that the derivative at that place would be undefined. It looks like we have a corner here. Okay. We also have places where we have local maxes, right there. And we also have a place where we have a local min here, and our other endpoint B. Okay. Now, we have these two values here where we don't have any extrema. However, what you should notice is that my tangent line there is still horizontal. And so we have a derivative of 0 there, but around 0, or around that c sub 1, the graph is rising, and then it kind of flattens out a little bit, and then the graph is rising again. So it's kind of like we could just sit a little egg right there on that shelf, and he would sit there, and we call this actually a shelf point. We also have a shelf point over here where you can see that the graph is falling, it levels out, that's the shelf, and then it starts falling again. But around those maxes and mins, for example this max, the graph is rising, or you should also see that the derivative will be positive, and then it falls, so the derivative is negative around that c sub 2. So we have a local max at c sub 2. So we have places where there are local maxes, where the derivative goes from positive to negative. We have places where we have local mins, where that critical value, it goes from negative to positive. And then we also have places called shelf points, where it might stay the same, positive to positive, or over here, negative to negative. Moving on. Here is basically what I just told you in word form. It says that the following test applies to a continuous function f of x. At a critical point C, if the derivative changes from positive to negative, then we have a local max. If it changes from negative to positive, then we have a local min. And if the derivative doesn't change, then we don't have an extreme value. We call that a shelf point. We also have talked about having extrema at endpoints, and at the left endpoint and at the right endpoint. And this is just saying if the derivative is negative, then we have a local max, that's on the left side. And if on the left side the derivative is positive after that, then we have a local min. We have at right endpoints, if the derivative is negative, then we have a local min. If the derivative is positive coming into B, then we have a local max. We have an example here of using the first derivative test. It says use the first derivative test to find local extreme values, identify any absolute extrema, f of x equals x to the third minus 27x plus 3. So to use the first derivative test, you have to find the first derivative. So we have seen over here that our first derivative is 3x squared minus 27 equals 0. And when we set that equal to 0, we get critical numbers of negative 3 and 3. So what we're going to do is figure out what is going on around negative 3 and 3. So we're going to make a sign chart to use the sign on each interval. The first derivative test and the sign of f prime tell us that there is a local max at 3 and a local min at 3. The local maximum value is 57 and the local min is negative 51. And we don't have to test endpoints in this case because our range, because our domain is all real numbers. The range is also all real numbers, so there's not any absolute extrema in this case. We're going to talk about another example, and we are going to welcome our fun little friend with the bow tie.
Let's use the first derivative test to determine the local extreme values of the function and identify any absolute extrema and support your answers graphically. What we have is y equals 2x to the fourth minus 4x squared plus 1. So we want to apply the first derivative test, which means we have to find the first derivative. So let's take and find y prime equals, well, this would be 8x cubed minus 8x. And now for the first derivative test, we need to know when is that equal to 0. So we set it equal to 0 and solve it. I can factor out 8x, which leaves me with 8x squared minus 1. So my two factors, this would lead to me to say that x equals 0, and this leads me to x equals plus or minus 1. So those are our critical values that we're interested in, the local, our extreme values. We don't know what they are yet, but that's what we're going to be looking at. Those are the extreme values that we need to check out. So what we can do is look at a number line. Here's 0, here's 1, and here's negative 1. What we're interested in is what is the value of the first derivative at these points. And what we have is the first derivative here will take some point, arbitrary point, like for instance negative 3, and plug it into here and plug it into there, and then evaluate it. However, I'm going to show you something that mathematicians do a lot. If I look at the factored form, it's actually a little bit easier to figure out if it's positive or negative. Because all I do is negative 3 in here. I don't even care what it works out to be as a number. I just care that it's negative, right? And the same thing here. All I care about is if this is positive or negative. Well, of course, if I take negative 3, that's negative. Here, it's positive. A positive times a negative tells me that in this particular interval, the first derivative is negative. Well, now let's look inside here, here, and here. And we'll do the same thing. So pick something like negative a half, and when you plug it into here and here, we'll find out that that's positive. And if I pick 1/2 here and plug it into here and here, we'll find out that overall it's negative. And then if I pick a number like 5, plug it into here, we'll find out that it's positive. So now we know what's happening with the first derivative. It's changing from negative to positive, from positive to negative, and then back again from negative to positive. Well, what does that all mean? What it tells us is that at x equals negative 1, this point right here, we're going to have, and I'm going to just sketch something for you, it's going to be some kind of local minimum. And at x equals 0, because it's changing from positive to negative, right, we're going to have some kind of a maximum. And then again, it's changing from negative to positive at 1, so we're going to have some kind of a local minimum. And the other thing that I can say is that there's no other sign changes here. So in fact, this value and this value are both going to be absolute minimums. And the way we can find out what they actually equal is to take the 1 and plug it back in here for x. When we do that, and I won't bother to do the arithmetic, but we will get y equals negative 1. So the absolute minimum value is y equals negative 1. Let's take a look at the graph to see if it supports these local minimum and the local maximum points that I've described to you just by using the first derivative test. So here's the graph. And look at that. Of course, it totally agrees with what we found. We have a local and minimum points at -1 and +1. We have our local maximum point at 0. And there, of course, were no other sign changes. And we can see that the value -1 for y is our absolute minimum value.
Okay, we are talking about concavity next, and we have a picture of x to the third right here, and what concavity discusses is the way the graph is bent. And so if you notice where the mouse is following this function, wherever I would draw a tangent line along this function, you should see that the tangent line would be above the graph of the function. Since the graph is below, we call this concave down. Now, at x equals 0, it now changes to where if I move my mouse this way, all those tangent lines are now below the graph, which means my function is obviously above, which we call that concave up. This place right here, at x equals 0, is called a point of inflection. That is where the concavity changes from down to up or up to down. The graph of a differentiable function y equals f of x is concave up if the first derivative is increasing, and it is concave down if the first derivative is decreasing. Now, what you should see that is here where the first derivative is increasing. We've talked about how increasing and decreasing functions are being reflected through their derivatives. Since the first derivative is increasing, it should follow that his derivative, the second derivative, would be positive, and that the second derivative, if the first derivative is decreasing, would then be negative. So our test for concavity is going to actually be using the second derivative, and it says the graph of a twice differentiable function f of x is concave up where the second derivative is greater than 0 or positive, and it's concave down where the second derivative is less than 0. We're going to use the concavity test to determine the concavity of x squared on the interval from 2 to 8. Now, we should at least recognize that x squared is a parabola who looks like, oh, let's see how good I am here, 2 to 8. I'll just draw the, okay, just pretend. Out here is 2, way out here is 8, and you can see that okay, so there's my graph. Since the second derivative is 2, right, the first derivative would just be x, or 2x. The second derivative would then be 2. Since 2 is positive everywhere, the graph of y equals x squared would be concave up everywhere. And in particular, then, it would be concave over 2 to 8. If it was negative x squared, which would look like this, then over 2 to 8 it would be concave down because my second derivative would be -2, and everywhere it would be negative. Now, within different functions, it doesn't always have to be concave up everywhere, concave down everywhere. This is just one example where that is the case. A point where the graph of a function has a tangent line and where the graph changes concavity is called a point of inflection, which we talked a little bit about in that on that previous slide where the picture, it basically just has to change from up to down or down to up in order to be a point of inflection.
Yay!
Use the concavity test to determine intervals on which the graph of the function is concave up and concave down. The function we're going to look at is y equals 2 times x to the 1/5 power plus 3. So let's find the first derivative and then the second derivative. Y prime, the first derivative, is going to be equal to 1/5 times 2, so 2/5, times x raised to the -4/5 power. The second derivative is found by the same process. Take the -4/5 multiply it times 2/5, and we get negative 8/25 times x raised to the negative 9/5 power. Now, in particular, for the value x equals 0, the second derivative is undefined, which tells us that something is happening at 0. So I'm going to use that to say, let's look at what happens to the left of 0, like for negative numbers. Y double prime for any negative number, for instance, take negative 5. When we plug a negative in here, when we raise it to that whole power, it's still going to remain negative. Multiplied by the negative, that means that this is positive. So by the same reasoning, if we take y double prime of some positive number, for example, 7, it's still positive here times this negative. This will be negative. What that tells me here is that this is going to be concave up, and this is going to be concave down. Then in terms of the graph, this is just a very rough sketch. We know that for negative, it's going to be concave up. But then something happens at 0 where beyond to the right, it's going to be concave down. So that's how we can use that second derivative test to help us draw the graphs of functions. Let's try another example. Let's take the example to find all the points of inflection for the function y equals x times e to the x power. To do this, of course, we need to take the first derivative, and let's do that. And after we do the first derivative, we'll find the second derivative. So in this case, y prime, we have to use the product rule because it's a function x times e to the x. So it's the first times the derivative of the second, and remember the derivative of e to the x is e to the x. Plus, we now take the second function, which is e to the x, and multiply it by the derivative of the first function, which is x, and of course the derivative of x is 1. So that's y prime. Let's look at y double prime. Y double prime. Well, we again have to take the derivative of x times e to the x, but we just did that, so we know that this is the answer to just this section. So it's x e to the x plus e to the x. But then we have to do the derivative of that, so the derivative of e to the x is e to the x. So this time, what we have in terms of the second derivative is y double prime equals x e to the x plus 2 e to the x. And then I can factor out the e to the x. I'm going to set this equal to 0 because what I want to know is what's happening with the point of inflection. And so I have e to the x times x plus 2. And that equals 0. And it equals 0 when? Well, when x is equal to negative 2. So the second derivative is equal to 0 for x equals negative 2, which tells me that that's going to give me my point of inflection. But what's the actual point? I need to take this number and plug it back into the original function, y equals x times e to the x. So my point of inflection would be this. Negative 2 is the x value, and the y value, I plug negative 2 in here and here, so I get negative 2 e to the negative 2. And that's my point of inflection.
All right, we also have a second derivative test for local extrema, and that second derivative test says that if the derivative at c is 0, and if the second derivative at c is negative, then we have a local max at c. And if the first derivative is 0 and the second derivative is positive, then we have a local minimum at c. So I'm going to draw a picture of a local max, explain what this is saying. Here is a local max, and obviously right there is C, okay? We would have f of c being 0, or f prime of c being 0, because the tangent line would be horizontal. And then because it is concave down, therefore it would be negative. The second derivative would be negative. So that's why we have a local max. So if it's concave down and a tangent line there, we have a local max. On the other hand, if we have a picture of a local min, down here is C, my slope line would be negative, or I'm sorry, my slope line would be 0, and then my second derivative would be positive because we are concave up over this interval. So if it's concave up and a horizontal slope, then we have a local minimum at C. Find the local extreme values of f of x equaling x to the third minus 6x plus 5. We're going to use the second derivative test to find this. So we need to find both derivatives. The first derivative is right here, 3x squared minus 6, and then the second derivative is 6x. When I take my first derivative and I set it equal to 0 to find my critical values, then I will get plus or minus the square root of 2 as those critical values. To find out if plus or minus square root of 2 is a max or a min, I take both of those values and I put them back into the second derivative. When I do that, for the negative square root of 2, I get a negative value. And for the positive square root of 2, I get a positive value. So because the second derivative is negative, we have a local max. And because the second derivative is positive, we have a local minimum. Here is just some different pictures talking about the different things that we've talked about in terms of extrema and concavity. This picture is in your book, but you can see just how the different graphs look. And I'm not going to go through every single one of these because we've talked about all of them, but this is a good picture of some things that we've talked about. You might want to just look it over. I think that is it for this section. So come tomorrow with questions. If you have any questions, hopefully you've written them down as we went through and done this, and this will make good sense to you. Have a good one, everybody. See ya.